Okay, a lot of you had trouble with the geologic time investigation, and so I am going to show you how the geologic time investigation should have been done. On one side, I'm going to have the actual investigation, and on the other side, I'm going to show you in the web pages where to go to find the information. Hopefully, this will let everybody understand a little bit better how to do this. So what I'm going to do is I'm going to break this series of videos into 3 separate videos, and so I'll include links to those. But the first one is to calculate, actually the first one is to figure out which isotope a radioactive isotope turns into after alpha decay, beta decay, or electron capture. The second, so that's going to be this. The second is to calculate the amount of radioactive parent isotope remaining after a certain number of half-lives have passed, and we'll also calculate the amount of daughter isotope that has passed. Then we're going to figure out how to determine the age of the sample. And finally, and we're also going to look at some common fallacies of radiometric dating. Things, in other words, things that people don't understand. And then finally, we're going to apply relative dating principles and figure out how to determine the order of geologic events in a hand-drawn geologic cross-section. And I'll show you how to do this not only for the one that's in your class, in your investigation, but also other ones, and I'll show you where you can find ones that you can use to practice with. So let's start by determining what daughter isotope is formed when a radioactive parent isotope decays by alpha, beta, or electron, alpha decay, beta decay, or electron capture. And that's, we'll scroll through this because you can read this yourself. But here is the first question. And to find the web page that this is all based on, go to this web page, and you can see the link right there. Click on your class, then click on class schedule, and what I would suggest doing is scrolling down to geologic time, which is right here, and then open this in a new tab or a new window, and by doing that you'll be able to see it full screen. So the first thing we're going to do is alpha particle decay. And the easiest way to find that is to search for that in the Geologic Time webpage. And you'll just hit Control F, you probably know that already, and then type alpha decay, or just alpha. And you come up right here, and the first thing you see is what an alpha particle is. And an alpha particle is 2 protons and 2 neutrons, or it says 2 neutrons and 2 protons. And what that tells us is that when alpha particle decay occurs, it results in the ejection from the nucleus of a particle with 2 protons and 2 neutrons. And when that particle is ejected, of course, the number of protons and neutrons in the nucleus drops by 2 each. So there's a total of 4 particles being removed from the nucleus, 2 of which are protons. Okay? Now, one of the things you're going to have to remember, and I'm going to, and actually I'll talk about beta decay and electron capture next, and then we'll actually go to figuring out what happens. When beta particle decay occurs, what happens is that a neutron in the nucleus explodes, and when it explodes into a proton, which stays in the nucleus, and an electron, which is ejected at high speed. And the beta particle is simply that high-speed electron. And what that means is that the number of protons, because a neutron is being turned into a proton, the number of protons in the nucleus increases by 1. The number of neutrons in the nucleus decreases by 1, which means there is a net zero change in the number of neutrons and protons. And remember, the number of neutrons and protons in the nucleus is called the atomic mass number. The third type of radioactive decay that we're going to talk about is essentially exactly opposite from beta decay. Instead of a neutron blowing up into a proton with the electron leaving, in electron capture, by the term capture, you can guess that an electron is brought into the nucleus, and that electron joins with a proton to become a neutron. So in that case, in the case of electron capture, the number of protons drops by 1 because it turns into a neutron, and of course the number of neutrons increases by 1. So again, the atomic mass number is going to stay the same, but now the atomic number, which remember is the number of protons in the nucleus, that is going to drop by 1. Okay? So how do we figure this out? Well, in alpha decay, if we have the atomic mass number up here and the atomic number here and the chemical element symbol right there, and for instance, this could be, just for the sake of argument, uranium-235, which has an atomic mass, that isotope has an atomic mass number of 235. That's the total number of neutrons and protons. And the atomic number, the number of protons in a uranium nucleus, is 92. And so that's what that is represented by. So what happens, probably the easiest way to figure this out, is that we take an isotope and subtract from it an alpha particle with an atomic mass number of 4, an atomic number of 2, and that means that the atomic mass number drops by 4, and the atomic number, the number of protons, drops by 2. And so we would calculate it by having the atomic mass number minus 4 and the atomic number minus 2. And so, as an example, if we had an isotope, an atom of ruthenium 100, which means it has a total number of protons and neutrons of 100, and a total number of protons in the nucleus of 44, we would get the new atomic mass number of 100 minus 4 is 96, and a new atomic number of 44 minus 2 is 42. Okay? And you can do this. The same methodology can be done for any example of atomic mass number. It does not matter what element or what actual numbers are here. The atomic mass number will always drop by 4. The atomic number will always drop by 2. Notice that because we now have 42 protons in the nucleus, we no longer have ruthenium. And this is a characteristic of all types of radioactive decay. You always change the number of protons in the nucleus, which means you change the atomic number, which means you change the element. So you will never start out and finish up with the same element. Okay? So that's that's alpha decay. Now if we look, and let's look now at the example that we have. And actually, we do have, I forgot that I put this in, we do have uranium-235. Its atomic number is 92, and you would write it the way that I wrote it a couple minutes ago in green. So the atomic mass number is going to be 235 minus 4, which is going to be 231. The new atomic number, since we started with 92 protons and we removed 2 of them, it's going to be 90. And if you look at a periodic table of the elements, and that's a very easy thing to find. Let's open up a new window and look up periodic table. You'll be left with any number of them. And if you look at this, you will notice right down here that TH, which is thorium, has an atomic number of 90. And so that is the element that you finish up with. Now, one thing I want to mention, in this exercise, I have to put this together in a way that the computer can grade. And I gave you some instructions in order to do that. You have to follow these instructions. These instructions are, first of all, in order to enable the computer to grade this correctly. Secondly, so that I can see that you know what you're doing. Third, so that when you do this, you're less likely to make mistakes. And fourth, because when you come back to this material to study it, you will look at what you did and you will see how you did it. And so that is why, in every case, I tell you that you be sure that you show how you arrived at any numeric answers. Okay, so if we go back to this first one just asks you for the answer. The second one asks you asks you to show your math. And so in this case, you would write 235 minus 4 equals 231, and 92 minus 2 equals 90. Okay. Now, you can write that down in a number of ways, and you'll notice that the computer sometimes, for many of you, marked it wrong, but I went back in, and because there's so many ways of writing this out, I went back in and checked it and made sure that you had the right answer. Another thing that I want to point out is that I am not going to make you figure out what these elements are. The goal of this exercise is to be able to figure it out, not to pronounce what the word is. And so you'll notice that I explicitly told you, just use the atomic symbol, not the whole name. I will not give full credit if you use the full name. Some of you wrote down thorium. You only got half credit, okay? I wrote it there explicitly, so you should be able to get the right answer. Okay, let's look now at beta decay. Okay, in beta decay, remember that an electron leaves the nucleus. And if we look over here, beta decay, this shows you how to do it. In beta decay, if we start in this case with carbon 14 with an atomic number of 6, that 14 is the atomic mass number, remember, then we are turning, there's a number of ways of doing this. One, we take the 14 neutrons and 6 protons in that the 8 neutrons and 6 protons in that nucleus, and we turn one of the protons, we turn one of the neutrons into a proton. When we do that, what happens to the number of protons? If we've created a new proton, then the number of protons has increased by 1, and that will now be 7. If we've turned a neutron into a proton, we haven't changed the total number of neutrons and protons, so that remains the same. Okay? And because we now have an atomic number of 7, if we look at the periodic table, we will find that nitrogen, N, has an atomic number of 7. So we put down N there. Does that make sense to everybody? Okay. Next thing, show your math for how you figured out what carbon 14 decayed into. So the first part, there's a number of ways you could do this. You could write 14 minus 1 plus 1, because we're adding, oops, plus 1. Plus 1 equals, of course, 14. Or you could simply have said 14 minus 0 equals 14. Or you could have simply said 14, the atomic mass number doesn't change, and I accepted that as well. For the atomic number, you would have had 6 plus 1, because you added a proton, equals 7. Is this simple? Yes, it is. Okay? I know you can do this in your head. I want you to write it down, or in this case, type it, so that later on, when you study this material, you will remember what you did. Okay? The next question is radioactive decay, in this case, electron capture. Okay? So now we're starting with potassium-40. Oh, and by the way, the reason that I chose these particular isotopes is that these isotopes actually go through these particular types of radioactive decay. Potassium-40 actually does go through electron capture. So electron capture for potassium-40 with an atomic number of 19, when you pull an electron into the nucleus, then it's going to join with a proton, and that proton will turn into a neutron. Because the proton simply turns into a neutron, there is no change in the atomic mass number, so it's still 40. But because a proton has turned into a neutron, you now have one fewer protons in the nucleus, so you now have 18. And if you look at the periodic table, you will find that 18 is associated with argon. Okay, there's the 18. So this is argon. Okay. And again, for showing the math, you could simply say, if you wanted, 40 does not change, and you could say that 19 minus 1, because you're subtracting one proton, equals 18. Okay, does that make sense to everybody? So that's how we do radioactive decay. You will do the same thing anytime you do radioactive decay. I hope everybody here has looked at old exams, and if you had, you will have discovered that this kind of question appears on every exam number 2 for this class. Okay, I'm going to stop this and set up for the next one.